talked about how polynomial, what a root of a polynomial is, how many roots it has, that a degree m polynomial has at most m roots. We had the polynomial division with remainder algorithm at the end of last time. And so now let's specialize a little bit to C. And when I say we specialize to C, we're often also going to think about R as a subset of C. In other words, a real polynomial is also a complex polynomial because every real number is also a complex number. So we're thinking about Cx, which is polynomials in one variable, univariate polynomials, and complex coefficients. Okay. So the first theorem that we're going to need is the fundamental theorem of algebra. So we're going to get sort of two versions of this. So we're not going to prove it. The content is that every non-constant polynomial with complex coefficients, and by that I mean either it, has legitimately complex coefficients, or we're thinking about it as something in C of x, but happens to have real coefficients. Complex coefficients has a root. So the proof involves complex analysis, and so we're going to skip that because it takes us too far afield. The one thing that we should note is that this theorem doesn't tell you how to find the root. It just tells you that every non-constant complex coefficients, there exists a root. Of course, when the degree is 2, you can find that root using the quadratic formula. When the degree is 3 and 4, there's strategy. And when the degree is 5 or more, there is no formula. This is the result of Galois. Haven't heard about it before. So Galois worked all this out when he was a teenager, proved that there was no formula for a degree above 5. Was advised to write it all down because he had a duel the next day. He stayed up all night writing down all of this, the proof of this theorem and all the other work that he did. And then he died in the duel at the age of 20. Anyway, we still remember him. He did very important work. So fortunately, mathematicians don't get in duels that often anymore. Okay, so as a result of this theorem, we can conclude that every complex polynomial, which is non-zero, has a unique factorization. And by unique, I mean up to the order of the factors. So that could be a constant polynomial, right? And it's multiplied by some linear forms. With each of these complex numbers. So there's a factorization like that. And you can see the proof of that, so okay, when we start, we can do an induction. When the degree is 1, there's not really anything to do, right? I'm just writing. Okay, so we're done. Okay. And we can put a constant times it. And we know what the root is. 1. And if we have a higher degree, by the fundamental theorem of algebra that we just stated, we can peel off, there exists some root, and so we can do division, or we can peel it off. Whatever root is given there exists a root lambda, and we can peel off that root and write it as a linear form with that root in it, z minus lambda, times some other factor, which has a smaller degree, strictly smaller degree, and then repeat. Right? And for uniqueness, well, if you have two such factorizations, suppose you have two such factorizations. Well, when z equals lambda 1, this first term is 0, so the right-hand side is 0. So one of these terms must be 0, so there must be a lambda 1 on this side too. And so then we just divide these two things by z minus lambda 1. Divide this side by z minus lambda 1. And we have that they're equal. The smaller numbers of factors must be equal. You can do induction. Now the only issue is that, of course, you can only divide when z is not equal to lambda 1. But if they're equal everywhere except at lambda 1, by subtracting one side from the other, you would get a non-trivial polynomial that had infinitely many roots, and so therefore it must be the zero polynomial. So that's not an issue. Okay, so that factorization is going to be unique up to the order of the roots. So now I just want to remind you about some things, some facts about the complex numbers that we'll need in what follows. So every complex number can be written in terms of two real numbers. It's a plus bi, with a and b real, and I equal to square root of negative 1. That's what we've adjoined. We can define the conjugate. So if z equals a plus bi, we can define z bar, the complex conjugate of z, to be a minus bi. That is, we just change the sign on the coefficient of the imaginaries. And this operation of conjugation commutes with multiplication and commutes with addition. If you think about the complex plane, so it's a two real coefficients, so I can think of it as a copy of R2. There's a real coefficient and there's an imaginary coefficient. And any z can be drawn as some arrow in that plane. The length of that arrow, of course, which we denote as absolute value of z, or the norm of z. That's the square root of a squared plus b squared. You can also obtain that by multiplying z by its conjugate. Okay. And a couple of observations. If I have a real polynomial and I have a complex root, then lambda conjugate is also a root, as we saw in this situation. Right? I is a root, and so is minus I. Also, if alpha and beta are real, we have another version of this, which is that x squared plus alpha x plus beta factors. So the complex thing always factors, right? But this, we want to know when it factors in terms of the real field. That is, when is there factorization into linear forms with both of the roots real? Well, of course, you know from the quadratic formula that happens if and only if alpha squared is greater than or equal to 4 beta. And then we get an analog of this unique factorization for real version. So, okay, so polynomial over the complex numbers can always be factored, can always be split up into a product of linear forms and a constant. We see here that if we're only allowing ourselves real roots, it can happen that we get factors that don't split up into linear forms, quadratic factors. And the point of this theorem is that's the worst thing that can happen. So if I have a polynomial with real coefficients, which is non-constant, then it has a unique factorization. Again, the factorization is unique up to the order of the terms. Multiplication in a polynomial ring is commutative. The unique factorization looks like some constant scalar, a bunch of linear terms, so the m linear terms, and then I have a bunch of quadratic terms. X squared plus alpha big M x plus beta big M. So that's a product of the real polynomial can be written always as a product of linear terms and quadratic terms, with each of all the numbers appearing here real. Okay, and also all the alphas in R and the betas in R. And whenever I have the situation that I need to use these quadratic forms, it's because the quadratic formula failed to give me a real answer. Right? I'm in this situation where this doesn't factor into linear forms. Okay. I'm not going to give a proof of that. So let me just say a moment about why we're talking about this. Okay. So remember that what we're calling end V, or L of V, or L of VV. This is the space of linear transformations from a vector space to itself. Right? Suppose I have a linear transformation that lives in there. A couple of things we can note about it. Right? I take this linear transformation, if I multiply it by itself, it doesn't matter what order I do that in. Multiplying it by itself means composing it, right? So this is linear transformation from V to V. The domain and the codomain always match up. I can always compose two linear transformations. In particular, I can compose one linear transformation with itself. So it makes sense to think about like f to the m for any power. That's a valid linear transformation. And I can also, scale it by something. And I can also add these things, right? So I can take a linear combination of powers of such a linear transformation. We can't see that. Let me write it over here. So if f is in and V, then anything of the form alpha I, f to the I, is also in NV. It's also a linear transformation from V to itself. Right? So what that tells me is I can think about such objects as polynomials. This is essentially the same as a polynomial, and I might be concerned about whether I'm dealing with real or complex polynomials corresponding to whether I'm thinking about real or complex vector spaces. And that's the reason we're caring about polynomials, is because we're going to analyze the structure of these linear transformations in endomorphisms of V using these results. Right? This is going to tell us about how to split it up into over the complex field, how to split things up into very simple pieces. And in the real case, this is going to be not quite as simple. The linear forms are going to end up corresponding to one-dimensional subspaces. The quadratic forms are going to end up corresponding to two-dimensional subspaces. But it's going to take us quite a while to get there. Okay, but this is sort of a preview for the spectral theorems. And that's why we're reviewing it now.